So we want to get at the concept of the curl of the electric field. Sorry, I needed to get a new pencil. So in words, it's the curl of the electric field. And this takes us to Stokes's theorem. Okay, so Stokes's theorem says that if we integrate a field, let's make it more general, a vector field A around a closed loop, that is the same thing as the integral of this curl function. Sorry, I'm starting to write I'm starting to write E for electric field. I want to be more general, so leave it as A. That's the same thing as the curl of this vector field dotted into a surface area element. So it's the integral of the curl over a surface, right? That surface has this loop as its boundary. That's Stokes's theorem. So, so the curl, what do we mean by the curl of a vector field A? Well, it depends on the coordinates, but it's in Cartesian coordinates, we'll get it from the usual matrix. Right, so we have derivatives in x, y, and z of the components of this vector field. So we have the x component, the y component, and the z component. And that gives us the derivative of the z component of the vector field with respect to y minus the derivative of the y component with respect to z. That is the x component of this vector field, right? So the result of the curl is itself a vector. The x component of the field with respect to z minus the z component with respect to x. This is the y component plus derivative of the y component with respect to x, derivative of the x component with respect to y. And of course, this is the z component of this vector. And this object is telling us about how the field varies as you, in some sense, circle around. So does the field curl around? Right. This is sort of the opposite of the divergence of a vector field, which says how does the field change radially outward. In this case, how does the field change as you circle around? And so we'll explore this further in the next few lectures.